Next bit, you have this thing here, where if I consider equilibrium table, mole at start or initial mole, I have 2.00 mole of N2, and then I have 6.00 mole of hydrogen, and you have 2.40 mole of ammonia at the very beginning, you see, allowed to reach equilibrium. So that means these are not before equilibrium. Your volume is 1 dm cube, which make your life easy because you're gonna have to do concentration instead of using mole in your Kc expression. At equilibrium, you have 2.32 mole of nitrogen. Mole at equilibrium, you have 2.32 mole of nitrogen. So it seems that when you started with this, then you end up with more of this. So the equilibrium has shifted backward because you produce more of the nitrogen. So how much extra nitrogen did you produce? You produce 0.32 because this minus this, 2.32 minus 2.00, you have produced 0.32 extra mole of nitrogen. When you think about mole ratio, the mole of H2 form over the mole of N2 form. Okay, I specifically put in the form because that's how you should be thinking about how much have you formed. All right, so from the equation, you have 3 mole of H2 formed for 1 mole of N2. You want to know the mole of H2 form, but you also know the mole of N2 form, which is 0.32. Started with 2, and now with 2.32. So this is the extra bit that you have formed. This is the extra bit that you have formed. How much extra have you formed for the hydrogen? It's going to be 3 times 0.32, which is 0.96. So this is going to be plus 0.96, 6.96. All right. Looking at that, and you know that the concentration at equilibrium. Of course, I haven't finished with the NH3 yet, but I'm just trying to see what I can do in a multiple choice paper. Divide by 1 dm cube. Okay, so it's going to be itself. And then 6.96 divided by 1 dm cube is going to be itself. And we know Kc is going to be concentration of NH3 squared divided by concentration of N2 to the power of 1 and H2 to the power of 3 based on the stoichiometric ratio. Don't forget the square and don't forget the cube. This is to the power of 1, so you don't have anything there. So we are looking for divide by 2.32 to the power of 1, which this one has. We are looking for 6.96 to the power of 3. 6.96 to the power of 3. None of this is 6.96. You see this? That is not 6.96. Okay, we got 6.96 based on what we know about from the mole ratio. The actual mole of H2 produced. 6 plus 0.96 is 6.96. You will get 0.32 if you don't do the multiply by 3, which means you don't know anything about stoichiometry. Okay, and you will get 6 if you don't consider that you actually produce more H2 as you produce more N2. So without working out this bit, you can get this as the answer already. So MCQ is all about your logical thinking, and halfway through you can check the answer. But of course, in the theory paper, you need to check everything. So this is what I'm going to do next. I'm going to find out the mole of the NH3 reacted. So you get the N2 because the NH3 had dissociated. From the balance equation, 2 mole of this give you 1 mole of N2. So 2 mole NH3 give you 1 mole of N2. I want to know the mole of NH3 reacted. I know how much N2 has formed, which is 0.32. So the mole of NH3 that had reacted is 2 times 0.32, which is 0.64. But this is reacted. This is formed. Okay, that's why you need to be very, very clear. This is formed. This is reacted. When you form it, you add it. When you reacted something, you take it away. All right, because you have lesser of it because it has reacted. Okay, so this is one thing that a lot of students couldn't get. And of course 1.76 divided by 1 because it's 1 dm cube given in the question. So this is mole per dm cube, which you can then sub in 1.76 squared. Even without doing this step, you could have seen this as the only possible answer because this is the only one that gives you 6.96 there. All right. Question 11 is also something related to this Haber process again. But what do we have? We have lithium reacting with nitrogen to give you solid Li3N. So you have solid Li3N, which is actually a giant ionic structure. So it's Li plus, 3 of it, and N3 minus and 1 of it, okay? So typically we don't write the formula as such. This is written as such to show you the charges, to show that there are ionic interactions, and to show you the LCM is 3, so you need 3 of these and 1 of these. At the start, A and B are closed. The left-hand vessel is evacuated. Middle vessel has this reaction, which is Haber process equilibrium. And then you have right-hand vessel contain lithium. Which action would allow the equilibrium mixture to contain the most ammonia? The most ammonia. So lithium can react with nitrogen to give you Li3N. Okay. So if you open up this valve, then the nitrogen can react with lithium. Okay. That nitrogen can react with lithium. That means you will have nitrogen forming something else apart from forming ammonia. It will compete with this reaction. So it will not give you more ammonia. It will give you less ammonia because some of the nitrogen reacts to form lithium nitrite, Li3N. So you don't want B to be open. You do not want B to be open if you want more ammonia, because you want this reaction. You don't want the other side reaction. So keep B closed, all right? Open B, well, I say open both, right? But I see open B. No, we want B closed. Otherwise, your lithium nitride will form. So B and D are out. So do we want to open A or do we want to close A? This is evacuated, so there's no A inside. I mean mixture of gases, which is your A, not option A, but your A. When you open this, you will increase the volume of the container. When you increase the volume of the closed vessel, your pressure will decrease, all right? So by opening A, you increase volume, therefore decrease pressure of the container, pressure of the reacting chamber. Okay, so you can think about that, and then you can think about what happened when you decrease pressure. What happened when we decrease pressure? So this reaction has 1 mole plus 3 mole of gas. So you have 4 moles of gas on the left hand side. And here you have 2 moles of gas on the right hand side. When you decrease the pressure of the reacting chamber, the system or the equilibrium wants to try and increase pressure. It will shift to the side with higher pressure. When you have more molecules of gases, it will be higher pressure, so it will shift backward. When you shift backward, you will favor this side, and therefore you will get lesser ammonia when you shift backward reaction. When you shift to the left, lesser ammonia is not what you want more ammonia. So you don't want it to shift to the left, you don't want to open A. So keep A closed, all right? So keep A closed. So that is your first one. You want B closed. Now you want A being closed as well. So therefore, we want to keep both A and B closed in order to maximize the yield of ammonia, in order to favor the equilibrium to the right-hand side. Question 12 is about variations of first ionization energy. Which statement about the element is correct? So first of all, we know that the biggest drop will be when you fill in a new shell. So there will be 1, there will be 2, there will be 13, there will be 15, 16, there will be 18 again, and then it's back to 1, which means this is 18, and this will be 15, 16, this will be 12, 13, which means this is 1, and then etc, etc. So there's also 1, there's also 18, and then you get that slight drop becoming less prominent, obviously, as you go further down, as you have more and more shells. But I've just filled in the group number based on the very apparent trend. The first drop between, I don't mean 12, I mean 2. The first drop between group 2 and 13, second drop between 15 and 16, and then the drastic drop because when you fill in a new shell, which is further away from the nucleus and therefore more shielded. So P and X are in the same period. Well, P and X are not in the same period, they are in the same group. This is below this. This is further away from the nucleus. It's got one additional shell. So period is wrong there. it should be. They are in the same group, they are noble gases. General increase from Q to X is due to increasing atomic radius. Q to X is due to increasing atomic radius. So Q to X is across a period. I mean, you're given this data for free in the data booklet, but you should already know atomic radius actually decreases across a period, okay? Because the size gets smaller across a period. For the same reason why the first ionization energy generally increase is due to increasing effective nuclear charge. So that is actually incorrect there, okay? The small decrease from R to S, R is 2 and S is 13. So this is group 2 and group 13, all right? It's due to decreased shielding. You fill in P subshell, whereas here you only remove from the S subshell. So we don't talk about the shielding there, about being decreased. We're talking about being increased. That's why it's easier to remove the electron from here, because they are more shielded. So decrease is incorrect there, which means D must be the only correct answer. U to V is 15 to 16. As you know, group 15 would be P3, group 16 will be P4. So P4, you fill in parallel spin. Now you pair them up, and it is this thing here. It is this thing here. The paired electrons repel more, and therefore it is slightly easier to remove the electron from here. That's why you get a small drop, second small drop between group 15 and group 16. That's the only correct answer. These are things you'll be expected to fully explain in a paper 2 or even a paper 4 theory paper, essentially, completely for like 3-4 marks probably. Okay. Question number 13. This is the greatest tendency. Okay, I think I used up too much space for my other working, but anyway, greatest tendency forming covalent compound. There's something called Fajan's rule. Not sure it's specifically in the A-level syllabus or not, but we're looking for small cation, highly charged. That means you have high charge density. That will lead you to high degree of covalency. Just think of your AlCl3. Your Al3 plus is very small, very highly charged, even though your AlCl3 is giant ionic structure in a solid state, but it's got a very high degree of covalency, all right? So it sublimes easily to give you the simple molecular AlCl3 in the gaseous phase, which can dimerize to the Al2CO6 dimer, all right? As well as you can also have large anion, highly charged anion. Okay, so you want large anions to become more polarizable. So this is more polarizable. This is more polarizing. The cation is doing the effect. The anion is the one feeling the effect. All right. So based on what I just said, we can really rule out neon, because neon doesn't really form any covalent compounds, just like all the other noble gases. They just prefer to be monoatomic, and as such, when we talk about electronegativity or tendency to form covalent compounds, the noble gases are out of the question. But amongst boron, magnesium, and potassium, based on what I just said, you can think of boron is in second period, and magnesium is in third period, and potassium is in fourth period. So boron is the smallest, and if it does form a cation, it's in group 13. It's also group 13. This is, okay, maybe I write on the side. Group 13, group 2, and group 1. So you can imagine if it does form cation, alright, then this is going to be the smallest, and it's also going to be the highest charge due to it being group 13. And it will be the most polarizing among all these three remaining options, and therefore based on Fajan's rule, it will be the most polarizing, and therefore it will be the one that has greater tendency to form covalent compounds. And in fact, you will know that they do actually form covalent compounds: BF3, BH3, BCl3, etc., etc. So we don't really think of them as being ionic in that sense, as a result of them being very polarizing if they do exist as cation. Therefore, they will tend to form covalent compounds despite them being in group 13. Alright? Number 14, elements Y and Z are both in period 3. Where the chloride of Y is added to water, it reacts and you get a pH 2, which is acidic. So we're talking about acidic chloride. When this chloride of Z is added to water, it dissolves and a solution of pH is produced. So we're looking at NaCl because that's the only one that does not get hydrolyzed. Alright, so this one is not hydrolyzed. Z is not hydrolyzed. Both chlorides hydrolyze in water, not Z. That's why your pH remains 7. Okay. Z is sodium. Z is indeed sodium, but Y is not magnesium because the magnesium chloride only partially hydrolyzes. When you partially hydrolyzes only, your pH is very weak. It's only around pH 6 or pH 6.5. So B is incorrect. How about this? Z is aluminium. We just established that Z is sodium. So Z is not aluminium. And besides, AlCl3 hydrolyzes, and it will give you around pH 2 or pH 3, which is strong acid. SiCl4 does get hydrolyzed to give you SiO2, which is a white solid insoluble in water, and you get HCl steamy white fumes because this reaction is very exothermic. And that thing is not hydrolyzed, it's just sodium chloride. Number 15, when you have chlorine reacting with hot aqueous sodium hydroxide, so this is your disproportionation. But because you're in hot condition, you're going to get Cl-1 and Cl+5. So they tell you get Cl-1, which is chlorine -1. This chlorine plus 5 is ClO3-. You will produce that as NaClO3 because you have Na plus and ClO3-. So that is your ClO3-, which is chlorine plus 5. So a factual question. Next bit, you have this is a salt. So we're looking at halide, chloride, bromide, iodide. So it contains the halogens, but because it's existing as a salt, the halogen exists as the halide ion. So when you have J, when you have acidified silver nitrate, you get a precipitate. Alright, get a precipitate, so it could be either of them. And you have excess dilute ammonia. So dilute ammonia can only dissolve silver chloride. You get a colorless solution. So that means must be Cl- because only silver chloride dissolves in dilute ammonia. Silver iodide does not dissolve at all. Silver bromide requires concentrated ammonia. Silver iodide, whether you have concentrated or aqueous ammonia, they won't dissolve. When you add excess nitrate, it's going to precipitate again because the nitric acid can neutralize the NH3. So what you have there is actually AgNH3 twice. Okay, this is example of a transition metal complex, which you will do in A2 transition metal chemistry. The HNO3 will neutralize the NH3. When it neutralizes NH3, you can have HNO3 plus NH3. It will form ammonium chloride. When you take away the NH3, then the NH3 disappear, then it will precipitate out again silver chloride. This can very easily be your theory level paper where they ask you to suggest what happened here or explain what happened here. It can also be a practical question, practical experiment paper where they ask you to do this, state what you observe, suggest what happened. Okay, so we know it's got to be chloride because of this observation here, all right, and not any of the other. Number 17, thermal decomposition of group 2 nitrate. We know that it does not give you NO. We know it does not give you NO. We know it does not give you NO. It gives you a brown gas, and this colorless gas which you don't see. But when you hit a solid and you get a brown gas, you have to test it with a splitter as well. And then the burning spleen, the burning spleen will It's glowing. Glowing means there's no flames burning, whereas burning, the flame is still burning. So it's got to be glowing spleen. Test for oxygen is with glowing spleen. So your glowing spleen will relight, or we will use the term rekindle, as you would have known for your test of gases. All right. 18. So this is about different volatility. This is to do with how easy to boil. The more volatile you are, the easier it is to boil. So the more volatile means the easier to boil will be chlorine, because as you know, chlorine, bromine, iodine, a gas at room temperature and pressure, a liquid and a solid. Alright, so this one already boiled before you reach room temperature. This one hasn't boiled before you reach room temperature and pressure. Alright, this is all down to van der Waals get stronger. It's got nothing to do with the covalent bond, because these are all simple molecular structure. What you're doing when you boil simple molecular structure is simply you move the molecules further and further apart. You're just breaking the weak van der Waals forces between the molecules. So what we have is the van der Waals get stronger in bromine than in chlorine, and that is a result of more total number of electrons in Br2 compared to chlorine, but there's a secondary factor which is to do with bigger surface area of Br2 versus CO2, and this is often the secondary factor that a lot of students miss when they talk about the van der Waals, when they discuss about van der Waals forces between the halogens, whereas these are all part of something you have learned in classroom anyway. Okay. So water and ammonia take part in a reaction. It produces ammonium ion. So you know ammonia is a weak base. A weak base dissociates in water to give you hydroxide ion partially. A weak base dissociates in water to partially dissociate or to partially ionize into OH minus. This is what it is. You form ammonium ion. Which statement is correct? Ammonia has a dipole moment because you got a lone pair there, whereas this one, the ammonium ion, does not have a dipole moment, but it is charged. Okay, so the charge there is a full charge, whereas dipole is a partial charge. You need to be careful. Yeah, dipoles are not full charges. This is a full charge, but there is no more dipole because the dipoles cancel out due to the tetrahedral geometry, and all four atoms are the same, but you have a full charge. All right. So ammonium is a molecule, ammonium is an ion, ammonia is definitely polar. All right. So this is incorrect. Ammonia is polar, and then obviously ammonium ion is fully charged. All right. So in terms of shape of molecule, earlier in the questions I talked about VSEPR, so I don't want to repeat this again, but this is essentially 107 degree with 3 bond pair and 1 lone pair on the nitrogen, whereas this one is 4 bond pair and 0 lone pair, because you count this as a sigma. So this is 1, 2, 3, 4, 4 sigma and 4 bond pair. Nitrogen has 5 outer shell electrons, uses 1, 2, 3, 4, 5, because this is additive covalent bond, uses everything for bonding. It's now tetrahedral, 109 degree. So this is incorrect. It changes from 107 to 109, or you would say 109.5, but I usually put down 109 and that's perfectly fine. This is not a redox reaction because this is what you call an acid-base reaction. As you will call this is a proton acceptor. This is the base, this is the acid, because it gives you the H plus, and then this becomes the conjugate acid, and this becomes the conjugate base. If you say that you have never heard of conjugate acid and conjugate base, I suggest you go through your specification under acid and bases. Under acid and bases in chemical equilibria, they say that you are specifically required to be able to define acid base, as well as using conjugate acid, conjugate base definitions or terminologies. Alright, so the water in fact is acting as an acid, and it will form you the conjugate base after you give away the H plus to the base.